Okay guys, in this video segment we're going to talk about whether or not a reaction is going to happen naturally, or basically is it going to be a spontaneous reaction if we put two things together. Okay. To do that we need to talk about something called free energy, or otherwise something also called Gibbs free energy. Okay. And when we deal with free energy, we're talking about any energy that is able to do work. Okay. So that could be thermal energy, it could also be energy from other sources, those kind of things. But basically, what is our available energy that we're using? Okay. If you have a reaction that releases free energy, it will happen spontaneously. Okay. If you recall, the whole purpose of all of our chemical reactions is to get to a lower energy state. So if a reaction runs that will release energy, meaning that the products have a lower energy state than the original reactants, then that will be favored, or it will be a spontaneous reaction. Okay. So that's one of the two terms that we use within this idea of whether or not a reaction is going to happen naturally, is the word spontaneous versus the words non-spontaneous. For spontaneous reactions, they will happen naturally, and they're always going to be product favored. Okay, they're going to release the free energy. For non-spontaneous, they will not favor product production, so they will be a reactant favored equilibrium, and they're not going to occur naturally. Okay, so they're going to end up absorbing free energy. Now, it doesn't mean we can't get the non-spontaneous reactions to run. We can make them happen. It's just not going to happen on their own without some sort of input from us, or some extra energy input, or changing some sort of parameters within that. Okay? So let's go back to this idea of having reactions at equilibrium. Okay? Because we have these equilibriums, we know that the reaction runs in two different directions. We have a forward reaction and we have a reverse reaction. The forward reaction could be spontaneous, or the reverse reaction could be spontaneous. Okay? In all scenarios, one of those two directions will be spontaneous. Okay? So between the two things, one direction is spontaneous, which means the other direction is always non-spontaneous. Okay? So if we take a look at this reaction, how I wrote it, we have heat plus water plus carbon dioxide making hexane plus oxygen. Okay? This is reversible. So if we take a look and say, well, which direction here is spontaneous? Okay? If you look, we're releasing heat over here, so running in reverse is going to be exothermic. That's a good sign. If you look at this, we have water and we have carbon dioxide, and we have hexane and we have oxygen. Well, I really wrote this kind of the opposite of a combustion reaction. So really, if you look at this, the spontaneous direction is going to be actually in reverse here, because these two together will spontaneously react to make water and carbon dioxide, okay, in a combustion type reaction. To put water and carbon dioxide together and to put a whole bunch of heat in to make this happen would be kind of a non-spontaneous things to happen, okay? Now, we can change what is spontaneous and what is non-spontaneous by playing with temperature, pressure, and other variables. Okay, for example, like sunlight, photosynthesis, those kind of things. Electricity is another thing that we can use to make things that are non-spontaneous spontaneous. Okay, that falls back a little bit to Le Chatelier's principle in terms of which direction is favored in the reaction, or could you push the reaction towards one side or the other. Well, what you're doing there really is you're changing which side is spontaneous versus which side is non-spontaneous. So if we increase pressure, or if we decrease pressure for gases, if we warm something up or cool something down, okay, those are the kind of things that we can actually force one way of the reaction to become more spontaneous. Okay. Now, typically people think of spontaneity and they think maybe back to this idea of it being exothermic, or that if you are an exothermic reaction, because you're releasing heat energy, that you have to be spontaneous. And that's not necessarily true, okay? So this last sentence question down here, is exothermic always spontaneous and endothermic non-spontaneous? The answer to that is no, okay? Absolutely not. Now, it is true that more often we see exothermic being spontaneous and endothermic non-spontaneous, but we do have non-spontaneous endothermic reactions, okay? For example, we did one in our last unit on thermodynamics where we put barium hydroxide with ammonium nitrate together, and those two substances got very cold. And they got very cold because they were endothermic, but it was definitely a spontaneous reaction. So we do have examples of spontaneous reactions that are endothermic, okay? Which means enthalpy isn't the only sheriff in town. It means that enthalpy isn't our only deciding factor here, okay? So our other deciding factor is something called entropy, okay? Entropy we symbolize with an S. And what entropy does is it measures the disorder of a system. I know it's kind of abstract, but it really does. It measures how organized something is. Okay. Now, the natural tendency in our world is to go towards disorder. Okay, so we want to have disorder. Okay, so we want high entropy. Okay, if you think about it, your room, probably that you live in and sleep in, that kind of stuff, is a good example of entropy at its best. Okay, so I'm assuming, and it's not general for everybody, but I'm assuming for most high school kids, it takes a lot of work if you want to keep your room clean. Okay, it doesn't just happen naturally. You don't walk in the room and go, "Oh, look, my clothes are folded today. Oh, look, my drawers are closed. Oh, look, my bed is made." I don't know how that happened, unless you have a really nice mom. That doesn't happen. Okay, so most people, they walk in the room and they're like, "Oh my goodness, it's like a bomb went off in here." Okay, that's because it's entropy. Over time, things just get more and more disorganized. Okay. You can put it back into place, but that usually takes a lot of energy input to keep things organized. Okay. Another example, our bodies. We are constantly fighting entropy. Okay. As you get older, your body is less and less capable of fighting off entropy. It basically is less and less capable of maintaining this really good cell structure and organization. So sooner or later, all of us are going to have things that break down. We get sick, things like cancers. We don't heal as fast. Our skin doesn't generate as fast. All that kind of stuff doesn't work as well because we can't fight entropy as much. Okay. So here's a couple images for that. If you take a look at the top one, if you have gas particles at any normal temperature, you'd expect them to spread out and fly all over the room because of entropy, because they're going to expand and spread out. You would never expect that all of them would be sitting in one nice little corner for gas. Okay. Same idea here. If you threw a whole wheelbarrow of bricks off of a truck and they land on the ground, you're not going to expect them to stack up by themselves, right? They're going to end up all disorganized. Okay, so being in a state of disorder is the more probable thing. Here's another really good one. Okay, if we take an ice cube at 0 degrees Celsius and water at 0 degrees Celsius, okay, we're at the freezing point and we're at the melting point. So we have freezing and melting there possibility. Okay. Between the two, what will be favored? Okay, so if you are truly at 0 degrees Celsius, will liquid water freeze into a solid, or will solids melt into a liquid? Okay, enthalpy can't answer that question, because if we stay exactly at 0, both are possible because there is no change in the enthalpy there in terms of what's going on. Okay, but entropy can answer that question, because between the two, between being a cube of ice and being a puddle of water, the puddle of water is less organized. So if you are sitting at 0 degrees Celsius and you have a puddle of water at 0 degrees Celsius, it will stay a puddle of water at 0. Okay? If you have a cube of ice at 0 degrees Celsius, it will actually slowly convert into a puddle of water at 0 degrees Celsius. Okay? Now, this is, of course, assuming that you're not adding any extra energy in or taking any extra energy out that could push it in one direction or the other. Truly at just sitting flat at 0 degrees Celsius. Okay? So that's entropy. Entropy is basically the way we measure disorder. And to be spontaneous, we want entropy. We want disorder. Okay? Now, if we take a look at some of these things that we can determine, well, what has high entropy and what has lower entropy. Okay? So some rules apply to this. Rule number 1, gases always have more entropy than liquids. Liquids are more than solids. Okay? So water vapor, liquid water, ice. Okay? The gas will always be more. More particles equals more entropy. Okay, so if you dissolve something to break it apart, like an ionic compounds, if you crush it up into small pieces, if you tear it up, any way you can generate more individual pieces or individual particles, that's a way to increase your entropy. Okay, dealing with chemical reactions, if you can produce more molecules, you will increase your entropy. Okay, so this reaction here, water breaking down into hydrogen and oxygen, we start with 2 parts. We have 2 molecules of water. We end up with 2 hydrogens and 1 oxygen. So this reaction would increase entropy because we're going from 2 to 3 total particles inside of here. Okay. Now each particle is smaller, which also then goes back up saying, well, smaller means more entropy. Okay. So in this case, we have a couple things going for it, but the big one is we go from 2 to 3 particles. So we're increasing our entropy there. And then last one, higher temperature is more entropy. The higher you are, the more energy you give something, the more chaotic the motion is. The more chaotic the motion is, the less organized it's going to be. Okay, so again, higher temperatures, less organization is going to be more entropy there. Okay, now General rule, if in doubt, if you can't apply these three things, you're not sure what to do, ask yourself the question, is it becoming more organized or less organized? Okay? The less organized it is, the more the entropy you have. Okay? So it's actually kind of an inverse relationship of organization and entropy are inverses of each other. The more organized you become, the less entropy. The more entropy is the less organized between the two things. Now, when we want to calculate changes in entropy, okay, this is really not a new equation for us. It's the same as we had when we did enthalpy back in thermodynamics, where we said if we want to know the change in entropy now, an S versus a delta H we used in thermodynamics, we can find the sum of all our products minus the sum of all our reactants. Okay, so it's an identical equation as we did for thermodynamics and enthalpy. The label is still the same. It's all that kind of stuff is still the same. Okay, so let's take a look at kind of a practice idea here. What is the standard entropy change when liquid water is broken down into hydrogen gas and oxygen gas? Okay, so we need some standardized values to do this. Okay, and we do have a table on the website for you, and you also want to use that when we get to doing our homework. Okay, now to do this problem, if we take a look at it, we have water breaking down into hydrogen and oxygen. We're going to apply the change in entropy is the sum of the products minus the sum of the reactants. Okay. Going to the table from the website, we would look up that our hydrogen has an entropy value of 131 joules per mole times Kelvin times 2 moles of hydrogen. Remember, we have to double that because there's 2 of them there. Plus our oxygen, which is 205 joules per mole Kelvin, and we have 1 mole of that. Okay, so moles cancels out of our math again, very similar to the thermodynamics. And then we're going to subtract our products. We're going to subtract our reactants. I apologize there, reactants. So we only have one reactant, which is water. Okay, so water has an entropy change of 70 joules per mole Kelvin. We have 2 of them, so we're going to multiply times 2 moles. And if we plug all this math in, moles cancels, we end up getting a change in entropy of 327 joules per Kelvin. Okay. So if we go from water to hydrogen and oxygen, our entropy change is a positive 327. So we're increasing entropy. Okay, increasing entropy is good in terms of spontaneity. Okay, so this predicts that this reaction should be spontaneous, that we should spontaneously take water and it'll just break apart into hydrogen and oxygen. Now we know in practice that doesn't happen. Okay, so even though entropy increases, something else must be blocking this from happening. Okay, don't forget enthalpy or heat is the other major player in this combination of what will be spontaneous, what will not be spontaneous. So this reaction, entropy would say, yeah, be spontaneous. Enthalpy must be saying, no, don't be spontaneous, because it must be a bigger factor than entropy is playing a role here. Okay, so let's take a look at that.
Okay, guys, that wraps up this session here. In our next session, we'll start taking a look at the comparison between enthalpy and entropy and how we can determine by their values if the reaction will be spontaneous or not. All right, thanks.